Hello everyone and welcome to today's webinar. My name is Tom Carpenter. I'm the CTO at CWNP, and today we're going to be talking about IoT protocols, an overview. And this will also whet your taste just a little bit for what CWSA is all about. So CWSA gives you an overview of really the IoT space, the wireless outside of just Wi-Fi. Now, while Wi-Fi is heavily used in IoT, and in fact, nearly every Wi-Fi only vendor has specific IoT marketing that they do, the reality is that in a lot of spaces, like industrial IoT and agricultural IoT and so forth, much of the IoT, if not most of it in many spaces, is actually non-Wi-Fi. And it's wireless, but it's not Wi-Fi. So for those of us that are really familiar with Wi-Fi, we may not be as familiar with some of these other protocols. The goal of this webinar is to familiarize you with these other protocols and some other information about what's going on in the IoT world and help you understand why it's important to understand these protocols. Of course, we're developing new certifications next year, as we announced at Wi-Fi Trek in Nashville. We'll be developing a Certified Wireless Connectivity Professional Certification, CWCP, which is going to be focused on the way these protocols work internally. And so we'll be looking, for example, at communication exchanges in ZigBee networks, LoRa networks, 6-slow P-WAN, and so forth. So we'll be looking at these different protocols and understanding how they work in detail in CWCP. In CWIP, another certification we're developing this next year, the Certified Wireless Integration Professional, we're focused on, okay, we've got all these wireless devices, Wi-Fi, non-Wi-Fi, all these different devices, and they're generating tons of data. What do we do with that? How do we integrate all of these systems together? So it will be exploring APIs, application programming interfaces, and things like that. So just to give you an idea of what's coming down the road after CWSA, so that you understand what's going on there. Now, if you want to review this again later, like all of our webinars, it will be archived on YouTube. Our channel is CWNP TV. That's CWNP TV, all one word. And you'll find the archive of all of our historic webinars there. Now, while Wi-Fi is, no question, an IoT protocol, I'm not going to go into detail on it today. We have an entire history of archives of webinars related to Wi-Fi, of course. Today, we're focused on some of the non-Wi-Fi protocols that are being used in the IoT space. Now, with that said, you can always reach us on Twitter at CWNP and at Carpenter Tom if you'd like to engage with us there. Again, this webinar will be recorded and archived on CWNP TV. Now, with that said, we're going to get right in. And what I'd like to do is start with some interesting insights here. So I want to talk about the barriers to digital transformation in logistics or supply chain digitization. So a lack of understanding of digital technologies and their impact is the number one barrier, according to Peerless Research Group, PRG, in 2019, to logistics supply chain digitization. Now, what are we talking about when we talk about digital transformation or digitization? Well, we're talking about taking legacy systems that were manual and converting them to automated, generally speaking, IoT-driven type systems. And it's really, really interesting to look at just 1 year and the changes that were found in the PRG research. So, for example, take a look on the right here at the fact that a lack of understanding of digital technologies was already known to be a problem in 2018, but it went from number 2 to number 1. So the more organizations get involved in digitization, the more they understand the reality that people don't understand how these systems work. Take a look at this one. The second one in the list in 2019 was resistance to change. That was all the way down at 8 in 2018. It jumped from 8 to 2. Now, why might that be? Well, I would suggest that a primary driver for that is people are starting to implement things. You know, you don't resist change until change is coming, right? So when change starts to happen, you start to experience resistance to change. And then notice that in addition, what was number 9, focus on incremental change rather than transformation, is tied for number 2. And what was not even relevant in 2018 is also tied for number 2, selected operations are too complex. So in other words, as people are beginning to implement it, they're understanding the complexity of what's involved. They understand that some knowledge needs to be there. Some people need to understand what they're working with to be able to, well, work with these things. And I'm not going to go through all the list here for sake of time, but I was very intrigued to see how that as people are beginning to implement it, the key things that are rising to the top is a resistance to change and therefore a desire to do incremental change rather than an overhaul, a forklift type modification to the way things are done. And the lack of understanding is paramount. It has come up even higher than ever before, and the complexity of these systems is becoming obvious. And so very clearly, we need people that understand these IoT technologies, these digital transformation technologies, if we're going to implement them well. And this is just within the supply chain world, right? This similar type of phenomena is taking place in other industries as well. Now, what is the value of the Internet of Things? This is an interesting question. What's it going to grow to? Interestingly, notice that factories, they're called in this report that we have here from the World Economic Forum in 2016, factories are predicted to have a low estimate of 1.2 trillion with a high estimate of 3.7 trillion by 2025. Now, regardless of whether those exact numbers are reached or even higher numbers or lower numbers, the thing that's interesting is to notice where things are happening, at least in 2016. And what we see is industrial is huge. Cities are next. Then there's the human. This is, your smartwatch, right? Your health monitoring devices, things of that sort. And then retail, then outdoor stuff, work sites, vehicles, homes, and finally, offices. So the key thing is the mass implementations are happening with factories or industrial manufacturing and with cities. And so that's where the big spend is occurring for these technologies. Now, part of that is because that's where there's the most benefit, at least in the perception of people. But all of these are key areas to watch as we move forward. So what are we really talking about when we talk about Internet of Things? Well, I've shared this with you in the past, some terminology I like to use to refer to IoT devices. I like to call them connected objects, and I'm not the only one. A lot of researchers, a lot of experts and professionals in the IoT space use this term CO, or connected object. And these connected objects can connect and interconnect in various different ways. So you can connect CO to CO, two connected objects that simply talk directly to each other. CO to service, so they're reporting back to a cloud or to a centralized service within your network. CO to user, maybe they're giving feedback directly to a user. Imagine, for example, that your smartwatch gives you a notification, right? Or user to service. So now this is the connected objects are reporting to the service, and then the user goes to the service to look at reports, to look at dashboards and things like that. So these are some of the integrations. This doesn't cover the entire collective possible set of integrations. So we could say CO to X, right? To indicate that they could connect to possibly other things as well. The point is that these objects are connected, and that's what makes them IoT. They're using internet technologies for connections, and hence they are IoT devices. They are connected objects. Now let's look at the knowledge areas, what we need to know about IoT. 5 knowledge areas of IoT, and this is defined according to research performed by university professors. They've said that we need to understand sensors, aggregators, communication channels, e-utility, and the concept of a decision trigger. So this is the way they defined it. You can call these whatever you want. Sensors, your end nodes, right? Your edge devices. Aggregators, things that bring data together and make it useful. Communication channels, the way in which this data is transmitted. E-utility, the applications or systems that process that data. And then a decision trigger, which might be a human making a decision or automated decision through artificial intelligence or expert systems or some other type of solution. The point is, you can call these whatever you want, but these 5 components are there. These are the terms used to define them by the university professors that developed this model. But the point is that whatever you choose to call them, the point is that they need to be understood, these 5 key areas. And of course, we'll talk a little bit more about these areas as we go along and the roles played by the different protocols. Now, Sensor networks then are used in a lot of different areas. And while not all IoT devices are sensors, all wireless sensors that communicate with internet technologies would be considered IoT devices. And again, to be clear, to make sure I'm phrasing it accurately there, all sensor devices that communicate using internet technologies would be IoT devices. So not all sensors are IoT devices, and not all IoT devices are sensors. But I want to bring that clarity here. Now, you can see then a lot of ways we can use these. They're used by smart cities. They're used in smart buildings. They're used for health monitoring and health solutions. They're used in industrial, agriculture, your home environment, just environmental sensors. So they have sensors that check the chemical makeup of water and report that information back. They have sensors that report soil moisture levels and report that back. There are sensors for farming that monitor pregnant cows, and based on their health vitals can say, okay, this cow is about to give birth. So the point is that there are many different ways that sensors are used in different industries and in different environments in order for systems to work well. Now, the big question then, and then we're going to get into some of the details of how IoT works. Why do organizations implement IoT? And the top 3 reasons, according to IoT Analytics, were safety, to make money, and to save money. Now, it's interesting. Notice the number 1 reason people want to spend money on IoT. It is to save money. 54% of people agreed that that's a primary reason they're implementing IoT solutions. The point is, they're looking at a lot of automation. They're looking at an improvement in the data that they have for better business decisions. These types of things help them save money. Of course, some of them do it to make money, right? 35% say that. 24% are actually doing it because they care about their people. Well, seriously though, 24% say is for safety. They're improving the environment from a safety perspective. And I mean, if you think about it, this could range from things like air sensors in buildings so that we can make sure that we have good air quality within our facilities. They could be devices that sense machinery that could be overheating, that could be in a failure state that could cause injury to someone, vehicles that might be in a state of disrepair that could cause injury to someone. I mean, the opportunities for improved safety go on with IoT devices. And so certainly that's a key benefit as well. But remember, the big thing is saving money. So if you're involved in an IoT project, I would suggest keep these 3 things in mind and always ask yourself these 3 questions as we're implementing this project. How do we save money? How do we make money? And how do we improve safety? Because those are 3 big drivers that companies report. And therefore, if we as engineers are focusing on those things to make sure our solution helps save money, make money, or improve safety, then we're probably hitting some key drivers that need to be addressed with the IoT implementation. All right, so let's talk practical IoT. We have our IoT devices, which could be sensors, any other number of devices. They're communicating with some type of networking protocol, and yes, wired is still used. I know we love wireless, but wired is still used. And then there's monitoring, alert, and control devices on the other end that may interact directly with IoT devices across the network or through a central system. So for example, the IoT devices may report back to a cloud environment, and then you go to the cloud and you see a problem, and so you click a button to make something change to resolve that problem. And then the communication goes back across the network to the IoT device. So for example, in industrial environments, IoT devices can be sensors, and they can also be actuators. A sensor detects. An actuator acts. It does something. And so an actuator could change settings on a piece of machinery so that it runs cooler or so that it runs warmer. The point is that you can, through your control devices, whether that's a laptop, a tablet, a mobile phone, your smartwatch, a desktop computer, you go to your control device, you access the cloud, you access the system, and you control the device. In small scale deployments, maybe you're controlling a device directly. You're just connecting to it across the network, looking at its information, and then controlling that. That might be seen in small businesses or something like that. But in large scale deployments, we're going to have it centralized. Now, obviously, we're not going to have to go look every 5 minutes. We're probably going to have alerts that are triggered, things that notify us when decisions need to be made by a human, some things that are decisions that are made automatically and you're just notified the decision was made. But the point is that this is the basic high-level architecture of what IoT looks like. You've got your devices, you've got some networking protocol they use to get to the network, and then across that network, they may be communicating with the cloud, they may be communicating with a local server, but they're communicating in some way. And then, of course, you have your analytics and control from your control devices. There are different ways to think about how IoT is implemented as well. For example, we have the 7-layer model by the IoTWF, which Cisco was very heavily involved in, as well as many others, where they define 7 different levels. Then there's a simplified 3-layer model that many suggest, where we talk about the perception layer, the network layer, and the application layer. The perception layer being the edge devices, where sensing occurs, for example, with sensors, the network, where communications occur, and the application, where the data is analyzed automatically, manually, and any way that you work with that data. And then, of course, we have the IoT domain model, where we have different domains. We break it apart into many different domains and work with those domains. There are standardized models. There are proprietary models. There are many ways to think about IoT, but it's good to have at least something like the simplified 3-layer model in mind. So you can ask, how am I managing my devices at the perception layer? In other words, how am I managing my edge IoT devices? And how am I managing with the network? And what protocols am I supporting? And then what application level things do I need to deal with? What databases are involved? What application layer protocols are involved? HTTP, for example, or HTTPS preferably. So what am I working with at these different layers? How does my system function at all of these different layers so that I can work with it, troubleshoot it, and manage it well? So when it comes to your wireless hardware, well, you have a couple devices, right? You've got the node, the edge device, and you've got base stations. Now, in IoT, oh my goodness, we have so many different terms. So this thing I'm calling a base station here because it's kind of a traditional term for the thing that all the wireless nodes talk to, right? So I'm calling it a base station. This might be called a gateway. It might be called a sink. It might be called a router. There could be many different terms depending on the IoT technology that you're implementing, but it's the same concept. It's the thing the IoT client devices or end nodes communicate with, okay? So these are the two devices, and what we want to talk about today is the protocols used between these devices. Now, these devices can work on different networks, so we have wireless body area networks, and I'm going to go through these networks rather quickly here. A body area network, medical body area network, body sensor network. These are all similar terms that are used. Usually 10 centimeter to 1 meter range. It's within your body. We use Bluetooth, NFC, RFID, proprietary technologies here. Then we have our wireless personal area networks. These are usually from 1 to 10 meter range. And again, Bluetooth, RFID, and other proprietary technologies might be used. So think about your personal devices that you want to interact with and have them interact with each other. And then you have your wireless local area network, which we're all familiar with, wireless LANs. This is not just Wi-Fi, although I'm picturing a typical Wi-Fi access role or bridge here. Anything that is local to a campus is a wireless network, can be called a wireless LAN. So a ZigBee network is a wireless LAN, okay? A Bluetooth network may be a wireless LAN. So the Wi-Fi people I think they feel like in their minds they've hijacked and they've taken wireless LAN and it means 802.11. But WLAN is not equivalent to 802.11. WLAN includes 802.11, but it can also include other protocols as well. Then you have your wireless metropolitan area network, or the WMAN. The big thing here is it covers a city, a larger region than just a campus, right? So we're dealing with the fact that this network spans the city and different devices around the city can connect to the network. And then you have your wireless wide area network. So while the wireless LAN might be in a building or on a campus, the wireless MAN is in a city. A wireless WAN is a region or even something that gives communication across the globe. So these are the different ways to think about it. So what protocols can our IoT devices actually use? Well, we can use cellular protocols like LTE and 5G. Now, I'm not going to go through all of these frequency bands here. This is to illustrate for you all the many bands that are used. So with FDD, we have all of these bands. With TDD, we have all of these bands, and periodically new bands are also introduced. So you can see we have quite a lot of use with LTE. And then if you're communicating with LTE, then you're going to use some type of an LTE cellular gateway possibly. Now, the way that works then is your wireless devices all talk to this gateway, and then the gateway is the thing that actually talks to the 4G LTE network. What this means then is you don't have to pay for all of your IoT devices to be LTE subscribers. Instead, you pay for your devices and link them to a gateway that is the LTE subscriber. So you might be using LoRa or ZigBee or something like that on your local network. In this case, because this is a Monet device, it's using a proprietary protocol they implement called ALTA. But if you have some protocol, whatever it is, on the local link at the edge, this gateway connects to LTE to give you your wide area connectivity. And then we have, of course, our 5 gigahertz frequency bands. Again, I won't go into full detail on all of them as well, but we have frequency range 1 and frequency range 2, or FR1 and FR2. FR1 is what we traditionally think of, you know, the 410 megahertz up to maybe a few gigahertz. But then FR2 is your millimeter wave technologies and those shorter wavelengths, so 24 to 50 some or even 60 gigahertz. Today, it's defined up to 52.6 gigahertz. Now, there's a table on the next screen. These terms define it. If you're watching this archived on YouTube and you want to take some time to look at this, I'd suggest pause it, kind of skim this, let it go forward to the next slide, look at it there, and then maybe go back and forth a little bit to take a look, because you might want to investigate this in more detail. I'm just exposing you to all the frequencies that are used. So here we see FR1. And they're defined as N1 through N90, not every number assigned a frequency band, but these are the new radio operating bands for 5 gigahertz. So you get exposure to that there. And this is FR2. Now, it's important to note that these may change. So these are updated as of August 2019, but from April 2019 to July 2019, several new bands were added in the FR1 space. So certainly these bands can change, but these are the ones as of today that are in use. So why would I use cellular? Well, I may want to use a service provider network for cellular for IoT, obviously standard mobile phone access, laptops and tablets, backup internet connections through routers, mobile vehicular access, and fleet tracking. All of these are things that might drive me to use a service provider cellular network. But then I can also use the private network, again, for IoT. So I might use a private cellular network. There's a lot of talk about that these days. A lot of different companies doing webinars on private LTE and eventually private 5G. So cellular is a tried and proven connectivity technology that works well and is very stable, and therefore it's very popular. What else might we use? Well, before we talk about what else, let me pause and talk about something important with IoT devices. Not all IoT devices, in fact, most IoT devices are not. Not all IoT devices are speed hungry, okay? So the thing that impacts speed on any wireless or RF link is modulation, coding, channel bandwidth, signal-to-noise ratio, signal-to-interference and noise ratio, and the number of spatial streams. Now, I'm not going to go into the details of all of those here. We have many other webinars that talk about those concepts. But the key thing is to understand that sometimes I'm fine with slower speeds. Low rate wireless can be good. Why? Well, maybe I'm in a noisy environment and I just need to get the signal through. So I really don't care about high speed data transmission. I care about the signal always getting through. Or maybe it's long range communications, right? The longer the range, the lower modulation rate that I use and so forth. And so for long range communications, I'm going to have lower data rates. Maybe there's just limited frequency bandwidth available. I don't have a lot of bandwidth. And so I want to use what I do have well. Okay, so these are all valid reasons to be okay with lower speeds. And the same thing with range. Range is impacted by the output power, the frequency band used, the antennas, and of course the desired performance. So if I want higher data rates, I have to have a shorter range, all else being equal. And I have lower data rates with longer range, all else being equal. So for example, here we see a Monet gateway and a Monet sensor, and it suggests, the Monet specification suggests a range of about 1,200 feet or 360 or so meters. This works in the 900 megahertz band. So that's quite a range, right? And the benefit is that we can use it over long range, and it's okay because it's a sensor. It's not transmitting gigabytes of information. It's transmitting a few kilobytes or less, maybe a few bytes of information periodically. And so for that reason, longer range can be beneficial. And you see then here some different technologies and the ranges they typically utilize. So we have BLE, Bluetooth, ZigBee, 6LoWPAN, Wi-Fi, proprietary 2.4 gigahertz stuff that's none of these, sub 1 gigahertz. The range goes up the lower the frequency, generally speaking. And this simply has to do with the ability to build receivers and antennas that can pick up the signal well. And then there's RF and power. And there are two ways to think about this. There's low power wireless and low power consumption. So low power wireless means we have low output power. We're not transmitting at high output power. Low power consumption means we've got good power management, right? So low power wireless includes really Bluetooth, NFC, ZigBee, ANT, which is a proprietary protocol, even Wi-Fi. Obviously, you're going to go shorter distances if you reduce the output power of Wi-Fi to a significantly low amount, but it can certainly be used over acceptable distances with low output power. And then power consumers for power consumption, the radio components, the CPU in the device, and any ASICs, local storage that might be used, wired ports that might be used, and any additional interfaces. In other words, the more stuff you put in an IoT device, the more power it consumes. This is why if you're building an IoT device that's going to be plugged into power, then using something like a Raspberry Pi, not too bad. But if it's going to run on battery, you probably want either a custom printed circuit board or a printed circuit board that consumes less power as you're building that IoT device so that you can get longer life off of battery, which becomes obviously a key factor when using battery-powered devices. So one of the protocols is 802.15, and really this is quite a few of the protocols. So as you can see on the right here, 802.15.4 is the foundation of ZigBee, 6LoWPAN, wireless HART or HART IP, ISA 100.11a, MiWi or MiWi as some say it. All of these are based on 802.15.4. Okay, so what's that tell you? It tells you that they may offer all the different frequency bands listed here on the left. So these are frequency bands in the 802.15.4 standard from the IEEE as possible supported frequency bands according to and constrained, of course, by your regulatory domain. Now, which one is actually used depends on that network layer protocol specification. The vast majority of ZigBee, for example, today is only in 2.4 gigahertz, although historically ZigBee has supported 900 megahertz and so on. So it depends on what that system supports as far as the channels that you actually will have available in the frequency bands, but these protocols can work across these frequency bands if supported by this specification. When we think of architectures, 802.15.4 can work in a star topology, so you kind of have a personal area network coordinator and all the devices talk back to it. You can also have a peer-to-peer topology, where all the devices talk to each other and one of them is assigned the coordinator, but they can all talk directly to each other. And then you could even have hierarchical views. So you can actually have topologies that are much more complex, and we connect effectively multiple stars together. And this is something we call a cluster tree, okay? So there is, in this case, a PAN coordinator in each of the clusters, and there is a first PAN coordinator that usually coordinates the whole cluster tree. But again, it depends on the upper layer protocols. The 802.15.4 standard does not specify the details of how something like this would be implemented, only that it can be supported by 802.15.4 devices. Now, Bluetooth is a solution that can also be used. In its history, there have been times when it was an 802.15.4, I'm sorry, an 802.15 thing, and then it quit being an 802.15 thing. It was really Bluetooth, then 802.15 tried to support it, then it just became Bluetooth. So Bluetooth is managed by the Bluetooth Special Interest Group, or Bluetooth SIG, and they've introduced some things in the recent years that really enhance its usefulness for IoT, such as Bluetooth Low Energy, or BLE, the ability to use it with very low power consumption, beacons, which are heavily used for locationing. Direction finding has been greatly improved as of 4.0 and then also 5.0. And then Bluetooth Mesh has also been introduced with Bluetooth 5.0. So a lot of enhancements in recent years that I think are going to lend to Bluetooth becoming a very, very common localized IoT protocol, the local link protocol used for IoT. As you can see, we can go up to 1,000 meters with it. Certainly, we can go 400 meters, even within buildings with some of the Bluetooth 5 stuff. So there's a lot of potential for enhanced utilization of Bluetooth in the future. A protocol that not everybody knows about coming from the Wi-Fi space, but it's actually very popular in industrial IoT, is long range, or LoRa. So LoRa is a standardized protocol that can be used. You can get devices that support it. You can get boards that you can use in building IoT devices that support it. And there's LoRa and LoRaWAN. This gets confusing for people sometimes. But the thing to keep in mind is LoRa is the wireless link. LoRaWAN is the communications on the other side of the wireless link across the whole network, right? Getting back to an application server or something. So LoRa works down there at the physical layer, and then LoRaWAN is dealing with how things happen in the upper layers, okay? So this is a key thing to understand. They're referred to as two things, but most people, when they talk about having a LoRa network, they're actually talking about LoRaWAN. So just keep that in mind as you begin to study this. You'll run into some possible confusion there. There are different classes of devices, Class A, B, and C. Class A are battery-powered sensors. Class B are battery-powered sensors and actuators. And Class C are main-powered actuators, so they're plugged into power in some way. So the difference is what they do, how they operate, based on the fact that they're either on battery or they're not on battery. As I said, ZigBee is very, very popular. And ZigBee, you'll notice we're looking right here at the specs for ZigBee, right from the ZigBee Alliance website. What I want you to notice is in the frequency band and channels section, what do they list? 2.4 gigahertz. They don't list 900 megahertz anymore. And so the reality is that it is in 2.4 gigahertz in most implementations, even with older stuff, because of the fact that that's supported worldwide. So it's easier to manufacture devices that work with it because of that. The other reality is that ZigBee has added support for ZigBee Green Power devices. So this is a new part of the specification that works with energy harvesting. So here, what we're talking about with energy harvesting, nice phrase and buzzword to know about. This is about pulling energy from the environment. It could be from vibrations, it could be from light, solar panels, right? It could be from wind, it could be from liquid flow through something. Any of these different things are energy harvesting. So we're converting some type of thing, activity in our environment, or a source like sunlight into energy, and then using that to power our devices. Then we have 6LoWPAN. This is all about getting IPv6 to work with 802.15.4 and IoT devices. So that's really what it's focused on. I'm not going to go into the great details of it today, but that's really what it's about. Thread is an example of an implementation of 6LoWPAN, really a specification based off of this that is commonly implemented. So Thread is what it's called, THREAD. Thread is a protocol that's commonly used to implement this. We have NB-IoT and LTE-M. We've already talked a bit about cellular, but as you can imagine, this could be really good for any type of smart city implementations and things like that, because we can run right on the cellular network providers that offer this. These are two different standards, NB-IoT and LTE-M, and LTE-M being the older, NB-IoT being the newer. And NB stands for narrow band, by the way. And so both of these are intended to be low rate. So they're not intended to be high data rates. So the big thing you hear about 5G is, oh, it's faster, right? It's faster. Well, the goal here is not to get data through faster, but to get data through and make sure it's consistent and stable, and therefore to have longer range because we're working with these lower data rates. The ZigBee architecture, some terminology just to know as we come routing toward our end of our overview of some of these different protocols here. In ZigBee, you have a ZigBee coordinator, a ZigBee router, and a ZigBee end devices. So the ZigBee coordinator, think of it as the master, the controller of the ZigBee network. And the router can bring different ZigBee end devices back to the coordinator through some route. And then, of course, the Z or the ZigBee end device is that end node that is actually doing whatever it's doing, controlling something, sensing something, what have you. So this is an example of a ZigBee architecture at a high level. Here we have the Z-Wave architecture. We haven't talked about it much yet, but Z-Wave based on ITU-T G9959 Phi and MAC. A lot of people don't know that, but Z-Wave is based on a standardized Phi and MAC layer, and it operates in 800 megahertz, 900 megahertz, depending on the region of the world you're in. So we have a Z-Wave hub or gateway, depending on which vendor implements it. They may call it by either of these names. And then you have the Z-Wave product. There's also a controller and a secondary controller. Now, the hub or gateway is generally the controller, and another device may also be a controller. The controller has responsibility for allowing devices to join the Z-Wave network and so forth, and managing the routing through the network and so on. This is mostly used in consumer space today, but we're starting to see more use of it in the enterprise space and industrial because of the fact that it's more secure today than it used to be. Then we have the LoRa or LoRaWAN architecture. LoRa architecture itself is peer-to-peer. LoRaWAN architecture is star of stars. And a very important note to point out, I don't know that you can see it. We're new to using Zoom for our webinars, but one person posted in the Q&A that indeed LoRa and LoRaWAN are two different things. I mean, LoRa is the modulation, right? So LoRaWAN is about how the network works. And it is possible you could have a LoRa device that won't talk to a particular LoRaWAN gateway. So you've got to make sure your gateways and your devices are, of course, compatible. And then there is possibly a LoRaWAN server on the back end that you're communicating with. So this is the typical architecture you might see in a LoRaWAN environment. You ready for the cellular architecture? This is nice and simple. Okay, you've got an IoT device. It talks to an IoT gateway that talks to the cellular network. That's what we see on the left-hand side here. So this is the gateway connect model. We also could have a direct connect model. The IoT devices simply connect directly to the cellular network. Maybe I'm using NB-IoT or LTE-M. Maybe I'm just using regular cellular, right? I'm just using regular LTE or regular 5G. The point is that these devices are connecting directly to the cellular network, and then it's up to that cellular network to provide us with access to whatever our destination is, wherever we're trying to take that data. Because they're, of course, able to route across the internet, we can get to any internet destination through the cellular network. And there are additional architectures. I'm not going to go into the details of them, but I'm going to mention them so you know they exist. We have, obviously, Wi-Fi, Bluetooth, Sigfox, Wireless HART, Digimesh is another proprietary one that's out there. N-Ocean, that's a specific energy harvesting solution for IoT devices. And so these are all different solutions. N-Ocean, by the way, works in the sub 1 gigahertz frequency range. So down there in 800, 900 megahertz, sub 1 gigahertz. Wi-Fi, Bluetooth, and ZigBee and 2.4 gigahertz. Just to remind you, these things all share this space. So the big gray boxes are your Wi-Fi channels. Hopefully that's the widest you're using in 2.4 gigahertz, 20 megahertz channels. The dark blue are Bluetooth and the light blue are ZigBee. Just to kind of give you a perspective of what this might look like. So the key thing is if we strategically use these channels, Bluetooth can get through, ZigBee can get through, and Wi-Fi can get through. Will they step on each other at all? Yeah, they may step on each other some, but they can all coexist in 2.4 gigahertz. And when it comes to IoT, in most cases, they work just fine because you don't need massive capacity for throughput of large amounts of data. You need reliable connection so that the data you are sending does indeed get through. All right, I want to wrap this presentation up with a dose of reality because my goal here today is not to talk about security in IoT, but I want to tell you a little bit about a report that came out. So F-Secure, you might know about them from creating antivirus software, but they do a lot of other security solutions as well. They have a honeypot network where they set up these fake network devices, right? Fake IoT devices. And they actually detected more than 2.9 billion attacks in the first half of 2019. Which was an increase of 300% over the same time the period the year before. So it's just their network, right? Same size of network as it was a year before, but now 3 times as many attacks as took place in the 6 months of the first half of 2018. What's that tell you? It tells you that people are targeting these devices more than before. And what are they trying to use? Mostly Telnet, SMB, SSH, MSSQL, and MySQL, and HTTP. There are other protocols too that might be utilized, but as you can see, those are the big ones. So if you want to make sure your devices are secure, a big thing to make sure of is that you don't have Telnet open, you don't have SMB open, you don't have SSH open, obviously, right? If you're not using it. So the point is that these things are locked down and secure. There are many attacks taking place out there. You want to make sure your IoT devices are not vulnerable. We'll talk more about IoT security in future webinars because it is a big, very important issue, and it will be an integral part of the CWCP certification as well. But just a dose of reality to wrap things up today. All right, at this point, I'd like to thank you for attending our webinar, and I look forward to seeing you again next month.